Now the second example where we have the source resistance as infinity, and if you notice here in this branch we have some RL as well, so we can also calculate the quality factor of that inductive coil anyway. So first question, determine all three frequencies Fs, Fm and Fe. So you know the formulas, so this calculation is quite easier. So Fs 1 over 2 pi LC, then the Fm was just Fs root over 1 minus 1 over 4, and for Fp and this 1 minus 4 is missing. So by using this calculation you find these values, and here it is also asked to compare their levels, so you can compare which one is higher, which one is lower, and how much higher, how much lower. And question B asks calculate the maximum impedance and the magnitude of the voltage Vc at Fm. So maximum impedance you need to calculate. So the calculation is easy because you need to calculate the total impedance that is present. So here in the above circuit, if I show you, so total impedance consists of this branch, that is the RL plus JXL, and this branch, that is the JXC. So you need to parallel combination of these two. So this thing is written here actually RS plus JXL and parallel minus JXC. So this is the maximum impedance, so if you calculate them individually, that is first of all XL, then XC, then obviously you have this RL plus JXL. Then if you if you apply the parallel combination formula, that is the ZT equal to Z on Z2 divided by Z on plus Z2 for two parallel branches. So through which you calculate the maximum impedance, and then you can also calculate the maximum voltage, that is Vc max, which will be I multiplied by Ztm. Now question C, determine the quality factor QP. So quality factor previously the formula is RS parallel RP divided by XLP, and since the RS equal to infinity, so it is just RP over XLP. So and if you notice, this is equal to quality factor of the coil. Okay, why? Because there is RS equal to infinity. So through which you can calculate the quality factor QP. And question D asks you to calculate the bandwidth. So bandwidth equal to Fp over Qp, simple calculation. And question E asks you to compare the above result when QL greater than equal to 10. So you already know that when QL greater than 10 we have some approximation. For example, first approximation, all these three frequencies are equal, so this is one kind of calculation. Second, QP equal to QL, just like here previously it was found 2.55, and also ZTP QL square RL. So these formulas are already derived in previous section, so I'm not saying all these formulas again. So when you calculate this, you will find some deviations so that are mentioned, and also they are discussed here, and probably in this math it is asked. Yes, so compare the above results. So you need to compare the results. What do you want to compare? The result you got by using QL greater than 10 and for the direct calculation here. Now example 21.8. so similar math is given where RS is available. So in previous circuit we have no source resistance RS, but in case of this example we have some 40 kilo ohm RS. So first of all, determine QL. So you know that QL consists of only this branch, right? So QL equal to just XL over RL, so you can calculate this one, and determine RP. So in question A you already found that QL greater than equal to 10, so you can use the approximation. Then by using this approximation, RP equal to QL square RL, so you can calculate this. And ZTP equal to just RS parallel RP, and also find C at resonance. So you know that at resonance our formula is simplified when we consider QL greater than 10, and we can consider this since this value is 25, which is greater than 10. So from this equation we can derive the equation of C just like this, where we can calculate the value of C. Question E asks find QP. So just like the similar approximation is used, so we can find the QP as well, just the similar formula previously mentioned. And question F asks calculate the bandwidth and cutoff frequency. So this is also similar procedure. Previously this calculation is already done, bandwidth, then cutoff frequencies. Anyway, so question now example 21.9. so this circuit is quite different from the previous ones, where is a transistor amplifier is showed here first of all. So this transistor collector, this is actually working here as the constant current source. So it is providing the 2 milliampere current. So if you redraw this circuit using some simplifications, then you can draw is as a current source which is providing 2 milliampere, and this 50 kilo ohm as it is written, this is the source resistance. So you can have a source resistance is parallel with the current source which is 50 kilo ohm, and this branch, so you can write is just like this, RL and C are in series, and this is parallel with the other branches. And then we have also the C in parallel. So this is the simplified circuit from which we will calculate the other values that are asked. So first question, find FP. So before finding FP, first of all we have calculated the quality factor also. So here Fs is calculated. So you know that Fs 1 over 2 pi root over LC, and then we can calculate the XL using that Fs, since XL equal to 2 pi FSL, and then quality factor equal to XL over RL. So we first calculate the quality factor. Since this quality factor is greater than 10, then we can use the approximation. So by using the approximation, we can write it that FP equal to Fs. So now this is Fs, that was the 318.31 kilohertz. So this is also equal to FP. And now they determine QP. So QP RS parallel RP XL, similar formula that previously shown. And then RP using the approximation we can write it QL square RL, and then QP equal to if you put these values here, so this is just calculated, and then the bandwidth is calculated, just the similar formulas. And also you need to determine the parallel voltage, that is Vp, and also sketch the curve of Vc versus frequency. So Vp, you know that Vp equal to, previously it was also calculated in other math, so Vp is just the current multiplied by impedance, right? So impedance is just RS parallel RP, and then you can calculate. And if you want to draw all this in a graph, so let's say this is the typical curve for Vp and bandwidth. So you already calculated bandwidth like this. So this is the bandwidth, and since it is QL greater than equal to 10, so you can obviously use the approximation. That means it is quite symmetric, and this portion you already calculated. Here the series resonance and the parallel resonance all are equal, 318.31 kilohertz. That means this point is basically 318.31 kilohertz, and this point is calculated just like previous series resonance math. That means since this is symmetrical, so this portion will be just bandwidth divided by 2, and similarly this portion, that means from bandwidth, from this point to this point we have bandwidth divided by 2 distance. That means and this value is calculated our Fp minus bandwidth by 2. So this one basically Fp minus bandwidth by 2, and similarly this one is basically Fp plus bandwidth by 2. And this type of similar math is already done in series resonance, so I think you will understand. And this is the Vp max that was calculated above, so it was 95.24 volt here, and you know that at the bandwidth condition we have 0.707 of maximum. So since it is voltage, so it will be 0.707 of Vp. So if you multiply 0.707 with 95.24, probably you will get 67.34. That's why this value. So now example 21.10. so you need to repeat the previous example but ignore the effect of RS. So I'm not explaining this since it is just like this previous problems. So when this rs is ignored, that means when rs is value is infinity, then there some approximation appears. For example, qp equal to ql, also the bandwidth changes, some changes appear just like a previous math I already shown. So you need to just compare those values here. And our last example here, where you need to design a parallel resonance circuit which have the characteristics just like this. So a characteristics is given, where is the maximum voltage given, bandwidth given, and also the parallel resonance frequency is given. So first of all, we can write the bandwidth equal to Fp over Qp. And here are some other values is also given. For example, the inductance value, inductance has 1 millihenry as the L value, 1 millihenry, and also it has a resistance series RL equal to 10 ohm. That's why the inductance is written 1 millihenry 10 ohm. That means it has an internal resistance of 10 ohm. And current source with an internal resistance of 40 kilo ohm. So the current source that we will be needing, that have an internal resistance of 40 kilo ohm. So first of all, the bandwidth equation we already know, that bandwidth equal to Fp over Qp. Then through which we can calculate the Qp equal to Fp over bandwidth. So Fp is given, bandwidth is also given in this figure. So we calculated the Qp equal to 20, through which we can calculate the XL 2 pi FPL as 314 ohm. From XL we can use the we can calculate the QL, because the QL consists of XL and RL. So that XL and RL through which the QL is calculated, and you know that Rp equal to QL square R for the approximation, since QL appears 31.4. So obviously QL greater than 10, we have found this. So we can use the approximation Rp equal to QL square R. So the values are given here. So Rp is calculated. Then Qp, so Qp was R over XL, and R was basically RS parallel Rp, right? And this thing is appearing in every math, so I think you already familiar with. So RS parallel Rp, so Rp was previously calculated, now this is RS parallel Rp, and Qp is actually already calculated, that was 20. So here is actually an equation arises, that means RS parallel this Rp divided by 314 equal to 20. So now if you write this just like this, so you can solve this equation and you find the value as RS. So RS you appeared as 17.298 kilo ohm, but in the problem it was already mentioned that the current source has the internal resistance of 40 kilo ohm. So source resistance 40 kilo ohm is already given, but to have this sort of characteristics, you identified that you need only 17.298. so how do you minimize that 40 kilo ohm? So obviously you need to reduce that resistance. So already 40 kilo ohm is available and you want it to have only 17 kilo ohm. So obviously you need some other parallel resistance, and then the combination of these two should be 17.298 kilo ohm. So this should be your problem. So let's say that parallel resistance is R prime. So obviously an equation arises, that means 40 and R prime, this is the R prime, 40 and R prime are in parallel to have a resistance of 17.298. By calculating, you found that R prime should be 30.48 and the closest commercial value could be 30 kilo ohm. So you define that we need a parallel resistance of 30 kilo ohm. Then at resonance, you know that XL equal to XC, through which you can calculate the values of C. So this is the commercially available value. So in this calculation, let's say you got 0.098. I don't know whether you will got this or not. So you will make this two closely commercial available, or quite a good figure, I can say 0.01. So then the ZTP, just like the previous one, ZTP is basically RS parallel RP. So this appears. So ZTP is calculated, through which we can calculate the I actually, because whenever we draw the network we will define how much current it will be delivering. So to calculate this I, we already know that VP over ZTP. So VP over ZTP, that's why this VP is already found. So ZTP, to calculate this ZTP, we have used this expression, that is RS per RP. So all values are given. I just calculated the R prime. RS was already given in question. This current is already calculated here, and these two values are already given, and this capacitance is calculated here. So this circuit is designed. That means this circuit will provide the response characteristics just like this. So far all the maths, all the example maths have completed here, and don't feel so much complicated because I just demonstrated the math. So if you feel these are complex, don't worry. Whenever you write them in your notebooks and whenever you practice them in your own, in your note, and whenever you calculate them, I think you will find easier whenever you will practice them as much as possible. So practice this math as much as possible. I think it will be easier for you. So I can end it here. Thank you.